So in section 9.2, we start looking at how the volume of a gas is affected by the pressure, the temperature, and the amount of the gas. And ultimately, we're going to come up with a master equation called the ideal gas law that relates all of these concepts. So the reason that we're having a particular chapter just devoted to gases is, of course, because gases are the only common state of matter that has a variable volume. So what are some things that affect the volume of a gas? Well, we've already identified that the pressure will affect the volume of a gas. And we said that if we apply a pressure to a gas, that we will reduce the volume. And that's, kind of seems pretty, obvious, right? So as the pressure goes up on a gas, the volume goes down. Now, what about the temperature of a gas? If I have a gas and I'm going to do my little trick of trapping it behind a piston, and then I heat it up with, say, a flame of some description. This is like a Bunsen burner flame here. Then what's going to happen to my gas? Well, you probably know that as gases are heated up, they expand, right? And you can test this out if you want to. What you can do is you can put a spray can full of gas in your oven and turn it on. And sure enough, it'll go kaboom and blow your oven up and possibly burn your house down. So please don't do that, actually. That's a bad idea. But what we do know is that gases, when heated up, will expand. So as the temperature of a gas is increased, its volume will go up. So what about amount? Well, let's think about this. As everything else is kept the same, if the pressure is kept the same and the temperature is kept the same, if I have a balloon, this is going to be difficult. I got a balloon and it's got a little bit of gas in there. And then that's a terrible drawing of a balloon. And then I blow into the balloon. What's going to happen to my balloon? Well, you guessed it. It's going to get bigger, isn't it? The volume is going to go up. So in chemistry, you probably remember that amount, the base unit for amount is the mole. And we indicate the number of moles of something using the symbol lowercase n. So what we're going to say here is, as the number of moles, as the amount of a gas goes up, what happens? Its volume goes up. So we have some qualitative descriptions of what we would expect. Pressure and volume are what we call inversely related. As one goes up, the other goes down. Temperature and volume are directly related. That means as one goes up, the other goes up. As one goes down, the other goes down. And number of moles, or amount of gas, and volume are also directly related. As one goes up, the other goes up. As one goes down, the other goes down. So you could see this. If I was to put a leak in this balloon, just introduce a hole. There's my hole. The gas would leak out, and sure enough, the balloon would get smaller in volume. Okay, so we already know this, right? We already know what's going to happen. We already know how pressure, volume, amount, and temperature are related. The problem is we don't have a formula that's going to tell us how these things are related. So what we want to do now is to look at exactly how these things are related. And we're not the first people to think of this. People were thinking about this for a very long time. And the first people to develop the equations that describe how these things are related were people that were interested in two big things. They wanted to make balloons so that they could fly, and they also wanted to make steam engines so they could power the Industrial Revolution. So the gas laws describe the mathematical relationships between pressure, volume, temperature, and amount of gas. And the first gas law to be derived, to be developed, was done so in the 17th century by a guy called Boyle, Robert Boyle. And sure enough, you guessed it, it's called Boyle's law. And what Boyle was interested in was how pressure and volume were related. And he knew how they were related. He knew that they were inversely related, and he knew that as the pressure on a gas went up, its volume went down. But he wanted to know the mathematical formula that related these things together. So what he did was pretty simple. He sealed a sample of gas in a J-shaped tube. J-shaped tube. There we go. And how he did it was by putting in a little bit of mercury. That's mercury in there, and leaving a little bit of gas there. So that's gas and that's mercury. And then he did something really clever. He added and removed different amounts of mercury, because the mercury is going to get pulled down under the effect of gravity to change the pressure on the gas. So it kind of looks like this. Here's your setup here, and here we go. We've got a fairly large amount of mercury here compressing this sample of gas here. The reason is the weight of the mercury is going to push down on here due to gravity, and that's going to apply a pressure. Right, remember, liquids can transmit forces to my sealed sample of gas. And if I take some of my mercury away, right, so I remove some of my mercury, what am I going to do? I'm going to lower the pressure on my gas, and sure enough, what did he observe? That the volume of the gas increased. So he found that as the pressure went down, the volume went up, or as the pressure went up, the volume went down, and that these guys are inversely related. Now, this was not much of a surprise, but what he did that was very clever was he used the scientific method. He put a little scale on the side here, and he also put a scale on the side over here, and so he could calculate how much the volume was changing and how much the pressure was changing, and he could make a nice graph of pressure against volume. So what did he find? He found that if you plotted volume against 1 on the pressure, you got a straight line with a positive slope. So this is what he says. This is what Boyle's law is. It says at constant temperature for a fixed amount of gas, right? Because the amount of gas is trapped behind that plug of mercury. The volume occupied by the gas is proportional to the inverse of the pressure of the gas. And so this is probably a little bit like, what does that mean? What do we mean by proportional? So volume is proportional, and to indicate proportional, we use this little symbol here, to the inverse of the pressure. And that what this means is this, that if you change volume by some factor x, you will change pressure by 1 on x. That's what that means when we use that language. So what this means is if I double the volume, I have to half the pressure. If I multiply the volume by 2, I'm going to have to multiply the pressure by 1 on 2, or a half. If I want to half the volume, 1 on 2, if I want to multiply the volume by 1 on 2, I will need to change the pressure by 2. So that's how that kind of works. All right, so mathematically, this is what I was trying to explain. For a fixed number of moles, so for fixed N, and for a fixed temperature, T, these are the symbols that we're going to use, the volume is inversely proportional to the pressure, or the volume is proportional to the inverse of the pressure. Now, it turns out when you do the math on this, what this means is that V is always equal to a constant divided by the pressure, or another way of saying that is that any pair of P and V, when multiplied, will always equal the same number. So if I have a gas at pressure 1 and volume 1, those multiplied together will equal a constant. And if I have a gas at pressure 2 and volume 2, those multiplied together will also equal the same constant. So sometimes Boyle's law gets summarized like so. Now here's the thing. you don't need to know Boyle's law and you don't need to know this formula. We're going to generate one master equation called the ideal gas law that has pressure, volume, amount, and temperature in it. And so you don't need to memorize this guy. But it is useful to think about how pressure and volume are related, and that as one goes up, the other goes down. Okay, so let's have a look at the next one. The next one's going to be how is temperature and how are temperature and volume related? Now, this was done by a guy called Charles, who is a Frenchman, because he was interested in balloons. And there are really kind of like two possible designs for balloons that were being considered around this time. One was the hydrogen balloon, where you filled a balloon with a lighter than air gas, such as hydrogen, and then you hung a basket under it and it would rise up. The other type of balloon that was being considered by the early aviators was one where you had a balloon that was full of air. You had a balloon that was full of air, but you kind of, you had some kind of fire under there and you warmed the air up, and that caused it to become less dense, right? So this is your classic hot air balloon. Okay, so these were the two things that people were considering. So Charles was, he was an avid balloonist. He actually took a balloon flight, or several balloon flights actually, but the first one he took was from downtown Paris, and it was interesting. They sold tickets so that people could see him take this balloon flight. The American representative, the American witness of this flight was a guy, you might have heard of him. He's called Benjamin Franklin. He's kind of a big deal. He was there to see this take off, and they'd got ready for these early balloon flights by sending up like animals to see if they would die. So they sent up, birds that could fly, and they didn't die, which was an unexpected. And then they sent up birds like chickens that were kind of thought to be like halfway between normal birds and mammals, because they were birds that couldn't fly, and they didn't die. So they thought, well, there's a possibility that mammals could fly. And then they sent up things like sheep and goats and stuff, and they didn't die. And they figured, well, humans and mammals, we probably won't die. So they decided in the 1700s they were going to send, or 1800s, where most of these flights took place, they were going to send humans up. So Charles set up a hydrogen balloon in the end in the middle of downtown Paris, charged money to see him take off. And he kind of reacted some iron with sulfuric acid. He inflated his balloon and he took off for his flight. He actually left from right in downtown Paris at what is now the site of the Eiffel Tower. So up he went, and they rose to several thousand feet very, very quickly. They got really scared. They didn't really quite know how to handle this situation, and they eventually decided that, and their ears were hurting and stuff, and it got cold, and they decided that they were going to let gas out. People were chasing them on horseback. They let the gas out. They did land safely in a field, and the villagers that were nearby, they didn't have a clue what was going on, and they thought it was like sky demons or something, and they kind of came running out with like pitchforks and started attacking these guys. But that was kind of the type of stuff that was going on at that time. But Charles's balloon was a hydrogen balloon that he ultimately flew in. Before that, he had been interested in hot air balloons and was studying how heat affected the volume of a gas, or how temperature in particular affected the volume of a gas. So what he did was experiments like this. He had a gas trap behind a cylinder, behind a piston, and he heated it up. And sure enough, what happens? The gas expands. And then you cool it down, and you measure the temperature as it cools down. And of course, as it cools down, the piston drops down. Right? Now, this is for a fixed amount of gas. It's a fixed amount because it's trapped behind the piston, and it's a fixed pressure because the only pressure that is on the piston is the weight of the piston being affected by gravity and the atmospheric pressure. So that is a fixed pressure on the gas. So you can heat this up, cool it down, and measure its volume, and you can make a graph of volume occupied against the temperature, right? So it's probably pretty obvious to you guys, as the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. These guys are directly related. So you can make a plot of volume against temperature. And I should point out that, by sort of like, it's a standard that whenever we write one thing versus the other, it's always interpreted as y versus x. So if you're ever asked to make a graph of something versus something, that's the order that they come in. It's a kind of reverse alphabetical order. But when you do this, you get a straight line. You get a line with a positive slope. So this is called Charles's law, and it says for a fixed amount of gas at a constant pressure, the volume of the gas is proportional to its temperature in Kelvin. So we say volume is proportional to temperature. And what that means is if you multiply V by some number x, you're going to multiply T by the exact same number. Now, it is important to recognize that this only works when the temperature is in Kelvin. So from now on in, it's important that you recognize that we're going to be working in Kelvin. And if you are given temperature in any other units other than Kelvin, you want to be changing that to Kelvin before you start doing any math. All right, so there's something weird about this, and you have to be careful not to interpret this incorrectly. What's going to happen at very cold temperatures? Well, at very cold temperatures, Charles's law predicts that if the temperature of a gas is 0 Kelvin, then the volume of the gas will be 0 meters cubed. Now, there is a little bit of a logical problem here. This is sort of like you're making an error here, because Charles's law applies to gases, and substances are going to change from being gases to being liquids well before 0 Kelvin, or to becoming solids even well before 0 Kelvin, at which point Charles's law doesn't apply and the volume becomes fixed. So don't kind of like get into the trap of, thinking that the volume of a gas will disappear or become 0 if you get it cold enough. Charles's law only applies to gases. Okay, so mathematically, again, for a fixed amount of gas at a constant pressure, the volume is directly proportional to the temperature, which means that the volume is equal to a constant times the temperature. And if I take the ratio of volume and temperature, that will be a constant. So what that means is that if I start with a gas at some volume and some temperature, that will equal a constant. And then I change the volume and temperature to some final volume and temperature. That will also, when you take that ratio will also be a constant. So people will often summarize Charles's law like this or like this, because those terms are just going to be equal to the same constant. Again, we don't need to know Charles's law, but in terms of the mathematics, we're going to have a combined, or what we call the ideal gas law, that we're going to be working with. But we do need to know that volume and temperature are directly related, and as one goes up, the other goes up, and as one goes down, the other goes down. Okay, we have one last thing to do, and that's to look at how the amount of a gas, which we're going to indicate by the number of moles, which we give the abbreviation lowercase n, and how that is related to the volume of a gas. This is described by Avogadro's law. I'm not going to give an elaborate story of how we got to Avogadro's law, but it's pretty obvious. We're going to keep the pressure and temperature fixed, and then we're going to add moles of gas to a container that can expand. So a classic example would be a balloon. And we're going to monitor how the volume is affected. And sure enough, what do you see? It's a dead straight line. And what that is telling us is that the number of moles of gas, and it's a straight line with an intercept at 0, is equal to a constant times by the volume. So again, we say the same thing, that the number of moles of gas is directly related to the volume, directly proportional to the volume. So that means if you multiply that guy by some factor x, you will also multiply that guy by some factor x. Okay, so that's Avogadro's law. So we've got our 3 laws. We've got Boyle's law, which relates pressure and volume. And what it says is that as the pressure goes up, the volume goes down. And then we've got Charles's law that relates temperature and volume. And what that says is that as the temperature goes up, the volume goes up. And then finally, we've got Avogadro's law, which relates the amount of a gas and to the volume, and we said as the amount of the gas goes up, the volume goes up. Now, this is of course the relationship between pressure and volume holds when we have a constant amount and temperature. The relationship between temperature and volume holds when we have constant amount and pressure. So basically, it's like varying one thing and keeping the other two constant. Okay, so these 3 things can be combined to give what we call the ideal gas law, and it's normally memorized in this format: PV equals nRT. R is a constant called the universal gas constant, sometimes also called the ideal gas constant. It's commonly expressed it's commonly written with 2 different units, which affects the numerical value. This is the value that we're most likely to use and is most commonly used when the problem involves pressure, volume, amount, and temperature. But this value is also used in problems concerning energies. So you do have to be aware of whether you're asking a question about energies or whether you're asking a question about pressure, volume, amount, and temperature. So when we look at the universal gas constant, it gives us a clue as to the units we need to be giving for the other things that are in here. So the pressure, the volume, and the amount, and the temperature. So clearly our amount needs to be in moles in order for this to work. Our temperature needs to be in Kelvin. Our volume needs to be in liters. And our pressure needs to be expressed in atmospheres. So if our pressure isn't in atmospheres, we're going to have to convert it. If our volume in our problem isn't in liters, we're going to have to convert it. If our temperature is not in Kelvin, we'll need to convert it. And if the amount is not in moles, we have to convert. Okay. So you can reorganize the ideal gas law, and you can see this, that if we divide both sides by NT, that PV on NT equals a constant for any gas, right, under any conditions. So if I have a gas under conditions 1, then the product of its pressure and volume divided by the product of the amount and its temperature will be equal to a constant. So P1 V1, N1 T1 will be equal to a constant. Now if I also have a gas, or if I change the conditions until conditions 2, then P2 V2 on N2 T2 will also be equal to the same constant. Or alternatively, we can say that the product of the pressure and the volume under conditions 1 divided by the product of the number of moles and the temperature under conditions 1 will be equal to the same expression for the gas under conditions 2. So this is useful because you can see in here that we have 8 terms, and if we know 7, you can solve for the 1/8. Right? So that's what we're really going to be doing. Now, sometimes you don't need to know 7 of these terms. Sometimes you just need to know that something is the same in both on both sides of the equation. So for example, if we were told that the temperature is constant, even if we weren't told the value of the temperature, we would be able to cancel out the temperature here. If we were told that both the temperature and the volume were constant in conditions 1 and 2, we could cancel out both of those terms on each side. And then, oh wow, that just looks like Avogadro's law. So what we can say is that we don't have to memorize Boyle's law, Charles's law, and Avogadro's law, because we can just cancel out the constant terms. Okay, so gas law problems are of 2 types. The first type is real easy. In the first type, there's no change occurring. You don't have conditions 1 and conditions 2, you just have conditions 1. And what's going to happen is you'll be given 3 of the 4 parameters describing the sample of gas, and you'll have to find the 4th. So here we go, we've got PV equals nRT, and say we know that the pressure equals 5 atm, we know that the volume equals 6 liters, and then we know that the number of moles is 2 moles. We might be asked, what is the temperature, right? So what we would have to do is reorganize this guy and solve for the temperature. Pretty easy. Now the only thing that's really kind of tricky here is that we have to remember our units. So R is 0.0821 liters atmospheres per mole per degree Kelvin. So we just got to make sure our volume is in liters, our pressure is in atmospheres, our amount is in moles, and our temperature is going to be given in the final answer in Kelvin. So as long as we keep our units straight, these problems are fairly easy. The second type of gas law problems is when a change is occurring and you're going from some initial state to some final state, or sometimes people will say you're going to go from state 1 to state 2, different ways of expressing the same thing. What's going to happen here is you're going to use this form of the ideal gas law, and what you'll do is you'll be given 7 of the parameters that go in here, and you'll be reorganizing, and you'll be trying to solve for the value of the 8th one. I should point out that your calculator has a feature on it called the solver. I'll post a video showing how to use that, and you can use a website, something like wolframalpha.com, where you don't actually have to you don't have to do algebra. What you can do is you can put in everything you know in an expression, and you can leave what you want to solve for just as x, and it will reorganize and solve for x for you. So that can be really, really helpful. I'll go through some examples showing you how to do that during office hours and problem solving sessions. Okay, so here we go here. A sample of gas in a 525 milliliter container at 1.25 atmospheres and 125 degrees Celsius is transferred to a new container with a volume of 825 milliliters. What is the new pressure if there is no change in temperature? So what's going to happen is it says here a sample of gas. So what that really means is that the amount of gas is not changing, right? So the initial amount of gas and the final amount of gas is the same, and that's worth noticing. The next thing is it says that there is no change in temperature. So that means again that the initial temperature and the final temperature are the same, and that's important. So what has changed? Well, the volume of the container changed from 525 milliliters to 825 milliliters. So what happened was that the volume of the container went up. It got bigger. So what do we expect to happen? Well, according to Boyle's law, we would expect the pressure to go down. So all we know about the final pressure up here is that it's going to be less than 1.25 atm. Now, this is a problem where we're going from some initial state to some final state, or state 1 to state 2. So we're going to do P1 V1 on N1 T1 equals P2 V2 on N2 T2. And the first things that we want to do is cancel out the things that don't change. So the number of moles doesn't change and the temperature doesn't change. So that makes it easy. Now, what are we trying to solve for? We're trying to solve for the pressure under the final conditions. So we've got to do P1 V1 on V2 will give P2, okay? And so now we just got to kind of like put our numbers in. Now, we get a little, well, let's just do it, huh? Let's just do it. We've got a hint. We know that the number has to be less than 1.25. So 1.25 atm times my V1, 525, times 10 to the minus 3 liters over V2, 825 by 10 to the minus 3 liters. Okay, so the liters cancels out, and it leaves units of atm, which is what we were after. So that's great. We're going to get this. So 1.25 times 525 divide 825 ends up being 0.795. Now, 3 significant figures all the way through here. So this is going to be 0.795 atm. And we're done. Okay, that's good. 0.795 is less than 1.25. Okay, so now we're going to introduce a concept called standard temperature and pressure. So this question asks, what volume is occupied by 1 mole of methane at standard temperature and pressure, which is often abbreviated by STP. Now, standard temperature and pressure in chemistry means a temperature of 0 degrees Celsius, also known as 273.15 Kelvin, and a pressure of 1 atmosphere. I think this sometimes is a little confusing because we often talk about standard state conditions, which is very similar except for T is 298 Kelvin. Standard state conditions is room temperature 25 degrees Celsius. So that's kind of like gets a little messy. Sometimes you do have to be aware of that difference. It doesn't come up very often. Okay, so what volume of gas is occupied by 1 mole of methane at STP? So the important thing here is that we realize that there's no change. So what that means is that we're going to use the first form of the ideal gas law that we saw, and we just have to think about what we have. We have the pressure equals 1 atm. We have the temperature is 273.15 Kelvin. We have the number of moles, N is 1 mole, and what we're trying to solve for is the volume. Okay, so this is just going to simply become that the volume is equal to nRT on P, and then we just have to sort of get all of our units straight. So we've got 1 mole, then the ideal gas constant, 0.0821 liters atmosphere per mole per degree Kelvin. I'm going to erase this stuff here. Then our temperature, 298.1, oh, there, no, see, I almost gave standard state, 273.15 Kelvin. And then finally, that's going to be divided by our pressure, which is 1 atm. So you can see that atm goes, ATMs go, moles on moles goes, kelvins on kelvins goes, and that's going to leave me with volume in liters. So when I do this, the answer I get is 22.4 liters. So 1 mole of methane at STP occupies a volume of 22.4 liters. Now, it turns out that this is true of any gas, because we didn't put anything in there that identified what gas it was. So 1 mole of any gas at STP has a volume of about 22 liters. So that's worth kind of just like keeping in mind to see if you're on the right track when you're solving problems. Okay, so here we go. This is what we did. We wrote out what we knew about the system, figured out what we wanted to solve. We took the ideal gas law. We recognized that no change was occurring, so we're going to use this form, reorganized to solve for the volume, and then we just put our numbers in and away we went. And then we recognize that this is a key result and that 1 mole of any gas at STP will occupy a volume of 22.4 liters. Okay, so we did it. We figured out the math that relates pressure, volume, amount, and temperature. We're going to use an uppercase P to indicate pressure. We're going to use an uppercase V to indicate volume. We're going to use a lowercase n for moles to indicate amount, because remember the mole is the SI unit for amount. And then we're going to use an uppercase T to indicate temperature. Now T in our calculations is always going to be in Kelvin. We have 2 forms of the ideal gas law. We can use PV equals nRT when no change is occurring. And we're going to use P1 V1 on N1 T1 is equal to P2 V2 on N2 T2 when we're changing from state 1 to state 2. Regardless of whatever form that we're using, we want to make sure everything is in the correct units that are going to work for us, so that's an issue. And in each case, all we're going to be doing is we're going to have all of the variables except for one, and we'll be solving for that missing variable. Okay, I hope that helps, and I'll see you around.